Hello, everyone, and welcome back to the next presentations at the Flight Software Workshop. Our next presenters are Tucker Taft and Tony Aiello from AdaCore, presenting SSI, SysML to Simulink to code. Tucker and Tony, it is all yours.
Thank you. Let's see if I can make, there we go, slideshow. So is that visible?
That's good. Yes, it is.
Okay, so I'm going to be reporting on some work we've been doing recently to integrate our Simulink TQL1 code generator we call QGen in with a model-based systems engineering. And we've used the term SSI, which is system to software integrity. And the point is that if you have a nice system design and you hand it off to the software development team, you would really like to have your system integrity preserved, the critical properties of the system preserved as you move into more detailed software development. So we've coined this acronym SSI, and we've used it both to describe this desired attribute, also a internal research and development effort at AdaCore, and also we've used it for the name of some of the tools we've developed as part of this internal research activity. So just to kind of give our view of model-based engineering, we see it as a way to create an overall model of your system and then successively refine that to build the actual product. And we're going to be focused on two aspects of it. One is at the system level, model-based systems engineering. And then as you get down into the software, model-based software development, which in our context means Simulink and Stateflow, but there's certainly other mechanisms people use to do model-based software development. So if you look at the systems level, this is where you really focus on the overall system requirements, the overall architecture, and if you're lucky, you can do some analyses at that level. And these days, there are more and more tools that are good for doing various kinds of analyses at the system level. Obviously, the goal is to find the problems early, to get the requirements right, to get the architecture right, and so on. SysML is an example of a system that supports this kind of model-based system engineering, and it's the one that we have been using for our internal experiments, and I'll report on those experiments now. On the other hand, there is model-based activity going on at the software development level. Simulink is probably the premier system for that, but there are many others out there. And we chose Simulink because we discovered that a number of our existing customers for Ada were already using Simulink. It's actually very widely deployed, both in aerospace and defense and in automotive. And those are two industries which are very important to us. And we chose Simulink and recognized that there was a need for a trusted code generator. That is something that could take your Simulink model and produce source code. And we chose to support both the Mistra subset of C and the Spark subset of Ada. And that's our QGen product, which we've been talking about, reported on in the past. So the question is how you link these two. And most commonly, you link it by throwing the architecture and some of the requirements over the wall. And then you sort of hope that they get implemented properly. But you begin to lose the connection there. And that's really what we've been trying to focus on, is trying to reduce the likelihood of losing that connection. And we'd like, ideally, to set up an automatic capability of translating some of those requirements and architecture into elements of the software design. And most, perhaps importantly, for various kinds of certification activities, provide traceability between your requirements and your system level architecture and the components of your software model. And you can go further if you begin to get a little bit more formal in the way you think about systems and in terms of specifying properties in a semi-formal requirements-based language. Then you could imagine that you could do stronger analysis at the system level. Same thing applies at the software level. If you begin to think in terms of formal methods, preconditions, post-conditions, invariants, and so on, this is a way to give you more confidence in the quality and correctness of your software development process. And in particular in simulation, you can create what are called synchronous observers, which basically just sit there and listen to your model as it evolves, as it's simulated, and check regularly that it's preserving the properties that you care about. At the software level, and also to some extent at the model level, you can do static analyses. formal proof, you can do model checking, and so on. And all of these rely on having some well-defined properties that you want to preserve. So now when we try to integrate into some of the systems level concerns, we're trying to connect those system level properties with the software level properties. And again, you can have kind of a throw over the wall approach, but what we'd love to have is, again, some translation, automatic perhaps, and some traceability for sure, to be sure that, okay, these are the properties at the system level, what are the corresponding properties at the software level, and are we preserving them, most importantly. You could also imagine skipping the model level, and if you have a high-level language that provides some amount of modeling capability in terms of pre and post conditions and variance and so on, you could also go straight from your system level properties to your contracts at the software source code level. So our view is that by combining system level requirements and properties with your software level model and properties, you can get a greater benefit out of model-based engineering. So putting it all in one slide, we have software architecture to some extent being reflected in the system level design. And we certainly have perhaps more formalized requirements coming down from the system level. And we'd like to inject those into the software level, in our case at the Simulink level, both in terms of monitors and also ultimately in terms of pre and post conditions at the generated source code level. So now I'm going to give you a chance for Tony to give us a demo of what we've done in this area with the Crazy Fly drone. And Tony, you want to say something about this this design here?
Sure. Although actually I was going to show a different model, so I apologize if that's
fine. I'll let you take it from here then.
All right, I'm going to interrupt your screen share and share my own.
Okay, well, let me stop.
So I will. Okay, so you can see my screen. Just let me move Zoom out of the way because it decided to overlay my screen. Okay, so what I'm showing here is the SysML model that we developed that I thought would be relevant for this audience. So we're not systems engineers, and this model was just meant to be representative in the sense that we wanted to demonstrate our tool. So what we have here is a high-level view of a triply redundant flight control system that you could imagine for an aircraft. So we have on the left a bunch of sensors, and these sensors have two different channels, a left channel and a right channel. And then we have some inceptors that are coming in, and we have a kind of distribution plane that's going to send this to the three different copies of our flight control computers. And each one of these channels is going to be running essentially the same code. So we expect in each one of these to have repeated elements. So we have redundancy management, which is taking in the left and right datas and voting on them. We have a state observer that's then giving us filtering of those inputs, and we have a control law. That sends out effector commands, which go up to some kind of a device that's going to sum these, for example. And so that's labeled actuators in this picture. So this is the high-level picture, and we've packed a lot of detail into these interfaces that are sitting behind the ports. So just briefly, I want to show you those so you can see that there's actually quite a lot going on here. So we have interfaces to represent air data, inertial measurements, and position, as well as inceptor commands in our state. So we've taken advantage of the feature in SysML where behind each one of these ports, we actually have a lot of data flowing. So this gives us the ability in the model to abstract away some of that detail, which we then intend to return in some sense to the software model when we get down to Simulink. So this is our starting point. And what we do with our tool is we come over here and we select rather the flight control computer. And we say we want to translate this to Simulink. So we'll go ahead and click that. And it's going to ask me to do this. Let me make sure I'm in the right place. So I'm going to say, yes, please go ahead and translate this to Simulink. And so this kicks off. And in the background here, you might have noticed that MATLAB kind of woke up and noticed that I was writing a bunch of files to it. So I've now asked MATLAB to help me create a Simulink diagram that has the starting points for the development of the software model that would implement the functionality of the flight control computer. So this is what I've generated. Let me pull it over onto this monitor so we can all see it. Now, this looks not quite like we would like. One of the difficulties in working with graphical languages is getting layout right. Layout algorithms in humans often disagree about what looks good. So I've manually adjusted this a little bit. I'll also make my window bigger here so you can begin to see that we have an appropriate structure. So if I zoom in here, you can see we have the redundancy manager components. Here we have the state observer component. I'll come back out. And here we have the control law component. And you'll notice that there's an awful lot of signals here. In fact, there's many more signals than we had in the original SysML model. Here we only had a handful of signals. But again, this is because each one of these signals in the SysML model actually had a lot of data in it. So if we zoom into the Simulink model, we can see that we've expanded these interfaces, and where before we just had left air data, now we've broken this out into discrete signals. We're showing you left air data, static pressure, dynamic pressure, air temperature, alpha, et cetera. And so we repeat all of this information coming into the redundancy manager. We could make different choices about this. We could instead turn these into Simulink buses if we wanted to. For this demo, we elected to turn each one of these components of the interfaces into discretes. So I'll save this because I've tweaked the layout here a little bit, and then I'll close it and get it out of our way. One of the other things that we feel like is important in this translation bridge from SysML to Simulink is to provide traceability so that engineers can see where elements of the model went. So I'd like to show that to you now. If I right-click on the redundancy manager, I can select highlight element in Simulink. It will open that model that we just looked at, and then it will highlight the redundancy manager component of that model in Simulink for us. So with a small model, of course, you can manually trace this, but as it gets bigger, it becomes increasingly difficult. And we can also pick individual ports, and we can do the same thing on individual ports and signals, which I won't show at the moment. Okay, there's one other thing I would like to show you. So this translation is meant to be durable. This is not meant to be a one-time, one-off just to get you started. Our vision with SSI was that this bridge should be bi-directional. I can't show you the reverse direction today, but what I can show you is that we can make incremental updates to the Simulink model that we generate. So I've kind of cheated, and using my undo buffer here, I have modified the model ahead of time. So there we go. I just redid a bunch of actions. And what I did is I connected a signal from the output of this overall control concept in SysML, and I routed it back around into this instance of our flight control computer. So I'm just wrapping my effector commands around, bringing them back into the input, and routing them into my redundancy manager. So of course, I would really want to do this 3 times so the redundancy manager could vote on all of my effectors, and then we could decide if one of these channels needs to be kicked off the island. Right now, for simplicity, I'm just going to stick with this one addition. So I'll right-click on my block. I'll say translate to Simulink. And so MATLAB wakes up, opens the model for us, and now what we can see is that we have inputs that weren't there before. So let me move these inputs around, and I'll scroll in. So here's 3 new inputs that we did not have before, these effector commands that I wrapped around. And what's nice about this is you can see that the changes to the model that I had made in layout were preserved when we added these new signals to the model. Okay, that's what I'd like to show you today in terms of a demo. So Tuck, if you would like, you can take the ball back.
there. Now you can see me and hopefully I'm not muted. So I just wanted to quickly wrap up, sort of describe the status of this prototype. We're missing error handling and reporting. That's usually one of the last things that comes along with a prototype. As you saw, we haven't got an advanced Simulink layout capability. We do better than we used to do, but it still needs help. And we haven't implemented the reverse translation. And finally, there are various conflicts. You can imagine you make one change on the SysML side, a different conflicting change on the Simulink side. The human has to resolve those kinds of things. The tools can handle things that are not interfering, but for things that interfere, clearly someone has to get involved. So to kind of give you a post-mortem, if you will, on this experiment, this was an internal effort initially. And our conclusion was to some extent that SysML wasn't quite ready. And furthermore, that systems, model-based systems engineering is more than just SysML. It's a lot of tools and people are doing lots of analysis at the system level. But one thing that is still true is coming out of this process, which maybe is more than just SysML, are things like architecture and system level properties. And those we believe are of interest at the Simulink level. So we've begun to really focus our energies on pulling and injecting system level properties into Simulink models and trying to validate Simulink models against properties coming down from systems engineering. So in future presentations, you will see us focused probably on that. But we found this a very interesting project, and we think in some ways we may come back to this someday when, let's say, SysML v2 has become more mature. SysML as it is just a little bit too, let's say, semantics free, or maybe semantics creative. That is, each user can use SysML in their own way. SysML v2, which is coming along very quickly now, has a much more well-defined semantics for all of the components. And that may be give us another chance to come back and reintegrate Simulink with some of these higher-level tools. But our goal ultimately is to validate Simulink against these system-level properties, both statically using things like model checking and proof at the generated code level, and more dynamically using things like synchronous observers. So with that, I will take questions.
All right, thank you both. We've got a couple of questions in already and several minutes for more. So first question from Chris, along the lines with bidirectionality, how do you do DIS and make the user aware of new signals?
Tony.
I can take that. Yeah, so diffs and bidirectionality, this was going to be really difficult. What we did is we looked for things in one model that we had not seen before on prior translation, and the intent was to carry them back to SysML and effectively give the systems engineer the ability to say, yes, I want to incorporate this into my SysML model, or no, I want to reject this. Now translation is broken and we have to repair it. And similarly with conflicts, we had strategies that we were exploring for conflict resolution, and we're going to do something similar, attempt to resolve conflicts gracefully when possible, and if not, say, I can't resolve this, you resolve it in the model, and then help me essentially reestablish the traceability links between the Simulink side and the SysML side. Did that answer your question?
I'll see if Chris chimes in on that one and let him know. Yeah.
He says yes, I see.
Okay, there we go. All right. So next question, is the system modeler fully your product, or is it third party?
The system modeler is not our product at all. I'm sorry, I should have been very clear about that when I did the demo. I was using Cameo, which was previously Nomagic's product and is now Dassault's product. So that was Dassault Cameo. And we wrote a plugin for Cameo so that we could get access to the model using their public API, and also make in this case, very moderate contributions to the user interface. So you saw the progress bar in the bottom right-hand corner, and you saw the contributions we were making to the menus. So that was, in some sense, bog standard Cameo, just with a plugin that we had added to it. And of course, on the other side, we were talking directly to MathWorks Simulink, again, through their public APIs. and essentially driving Simulink through scripting at that point. We have not yet made contributions to the Simulink to the Simulink user interface, although that would be something we would have needed to do to support bidirectional translation.
And we do have Simulink plugins for our QGen product, so it's something that we have done in the past.
Okay, and next question from Colin Helms. The hard questions come up when code isn't working. How would the round trip synchronize between Simulink generated code, most likely edited and or patched by human programmers, and the original SysML model?
Right, so the vision was indeed that humans would make changes to the Simulink. So again, I apologize if that wasn't clear in the demo. We were trying to create a skeleton, a starting point for the controls engineers to then complete the design of the software, to complete the algorithmic development of the software. And so it was always the intent, in fact, that the Simulink would be edited. And let me rearrange the layout and then generate some additional signals. In some sense, that was also to illustrate that we were able to cope with changes made to Simulink. I did not, but could have added additional blocks to the Simulink model, and still we would have brought in new contributions that were coming from SysML. So our vision was always that there would be this work that would happen. Our tool would detect new things added, and then in essence, ask the software engineer or the system engineer to say, hey, this new thing that showed up, is this an implementation detail? Or did you want this in your system model? Should this be reflected at the level of interfaces so that it can be carried forward in subsequent iterations of the design?
Okay, next question. Can the Cameo system modeler be tuned to work with UML diagrams?
The simple answer to that question is yes. Cameo it's kind of first and foremost a UML product, and SysML is a contribution or a capability built on top of it. That being said, we were processing the SysML model. We had not explored yet UML specific or base UML. It's a bit weird to talk about because SysML is a profile of UML. We hadn't dealt with like basic UML. We were trying to stick specifically with targeted elements of the SysML profile.
Okay, we've got a few more minutes left. Give just a few seconds for any other questions to come in. All right, Tony and Tucker, thank you so much for your time today. And yeah, thank you.
Thanks a lot.